Hello everyone, I welcome you all to the course of heat transfer. In today's class, we will discuss the derivation part of LMTD for parallel as well as counterflow heat exchangers. Now, we have already discussed LMTD is nothing but logarithmic mean temperature difference, which if we keep that constant, it will give us the same rate of heat transfer as actually occurs under variable conditions. Now, before looking into the derivation part, we have some assumptions. The first one is the overall heat transfer coefficient U is constant. Second one is the flow conditions are steady. Third one, the specific heat as well as mass flow rates are constant throughout. Next is change in potential energy as well as kinetic energy are negligible. Fifth assumption is no loss of heat to the surrounding. It means the heat exchangers are perfectly insulated. The last assumption is that no phase change of the fluid will occur. Now, if you see, this is the schematic line diagram for the parallel flow heat exchanger, and this is the schematic line diagram for the counterflow heat exchanger. We have already discussed in case of parallel flow heat exchanger, hot fluid as well as cold fluid move in the same direction. You can see here the hot fluid is moving from left to right. Similarly, the cold fluid is also moving from left to right. So when they are moving in the same direction, we call that as parallel flow. Whereas in case of counterflow, the two fluids will move opposite to each other. The hot fluid is moving from left to right, whereas the cold fluid is moving from right to left. When they are flowing opposite to each other, we call that as counterflow. Now we have some notations here. So this is TH1, TH2, TC1, TC2. Now TH corresponds to the hot fluid, temperature of the hot fluid. Tc corresponds to temperature of the cold fluid. Now suffix 1 represents the inlet condition and suffix 2 represents the outlet condition. Now if I say TH1, this is the temperature of the hot fluid at inlet. TC2 is temperature of the cold fluid at the outlet. TC1 is temperature of the cold fluid at inlet. TH2 is temperature of the hot fluid at outlet. Now this nomenclature is same for counterflow as well. Now for our analysis, we have considered a small elemental area on the heat exchanger. of area dA. Now, the temperature difference at the inlet conditions is given by theta 1, which is Th1 minus Tc1. Similarly, theta 2 is nothing but the temperature difference at the outlet condition Th2 minus Tc2. This is true for parallel flow heat exchangers. Now for counterflow heat exchanger, theta 1 is nothing but Th1 minus Tc2. The temperature difference at the length equals to 0. Now at length say L, theta 2 is Th2 minus Tc1. Now consider a small elemental area of the heat exchanger dA. We know that the rate of heat flow through this elemental area A dA is given by del Q is equals to U dA into Th minus Tc. Now this is the temperature Th. This temperature corresponds to Tc. Now we have considered this to be theta. Theta is equals to Th minus Tc, or I can consider that as delta T. Now del Q I can replace as U into dA into delta T, where U is overall heat transfer coefficient, dA is small elemental area, and dt is the temperature difference between the hot fluid as well as cold fluid. Now whenever fluid transfers heat, one should lose heat and other fluid should gain heat. Now if you consider the energy balance, the hot fluid is losing the heat and the cold fluid is gaining the heat. It means I can equate the amount of heat lost by the hot fluid is equal to the amount of heat gained by the cold fluid. Now if you write that equation, it is nothing but mCp into dph. This is the amount of heat lost by the hot fluid. mCp into dTc is the amount of heat gained by the cold fluid. Now here we have denoted m suffix h, Cp suffix h. This corresponds to the mass flow rate as well as specific heat corresponding to hot fluid. Similarly, m suffix c, Cp suffix c corresponds to mass flow rate as well as specific heat corresponding to cold fluid. dTh is change in temperature corresponding to hot fluid. dTc is change in temperature corresponding to cold fluid. Now the one fluid has lost heat, another fluid has gained heat. Now if you see, del Q is equals to minus mH Cph into dTh we have written, whereas for cold fluid it is m dot C Cpc into dTc. Now you may ask a question, why there is a minus sign? The answer to this is, if you go along the length of the heat exchanger, the temperature is dropping. Now if you see here, if you consider this to be along the length, now if you go along the length of the heat exchanger, the temperature is dropping. along the length of the heat exchanger, the temperature is negative. Hence, we have considered for hot fluid minus m dot h Cp of h into dTh. It also gives us an intuition regarding the heat has transferred from the hot fluid. Once heat is transferred from a system, it is considered to be a negative. Once heat is added to the system, it is considered to be positive. This is the nomenclature that we have studied in basic thermodynamics. Now, if you get the expression for dTh, it is minus dq divided by m dot h into Cp of h. This can be written as minus dq divided by capital C suffix h, where capital C is heat capacity. It is given by the product of mass flow rate and specific heat corresponding to hot fluid. Hence, C suffix h is equals to m dot h multiplied by Cp of h. Similarly, dTc can be written as dq divided by m dot c into Cpc. This can again be written as C suffix c, where C is nothing but heat capacity corresponding to cold fluid. It can be written as the product of m dot c into Cpc. Now we have already defined theta is nothing but the temperature difference between hot fluid as well as the cold fluid. Now if theta is Th minus Tc, then d theta will be equals to dTh minus dTc. Now if you consider these two equations and if you take the difference of these equations, dTh minus dTc is equals to minus dq divided by ch minus dq divided by cc, minus multiplied by dq is taken out 1 upon ch, so minus of minus plus 1 upon cc. Now here, this is nothing but d theta. I can consider this as d theta is equals to minus del q into 1 upon ch plus 1 upon cc. Now we need to substitute the value of 1 upon ch and 1 upon cc in the subsequent steps. Now before that, what is dq? dq is nothing but u into dA into Th minus Tc. We have considered this to be the first equation in the beginning, where u is the overall heat transfer coefficient, dA is the small elemental area, Th is the temperature of the hot fluid, Tc is the temperature of the cold fluid. Now I can write this as theta. So d theta is equals to minus u into dA into theta multiplied by 1 upon ch plus 1 upon cc. Now if you separate the variables, d theta by theta is equals to minus u into dA multiplied by 1 upon ch plus 1 upon cc. Now if you integrate the equation from state 1 to 2, so you have integration of 1 upon d theta, which is nothing but ln theta. The values are varying from 1 to 2. You will be having ln theta 2 minus ln theta 1, which is nothing but ln theta 2 by theta 1. It is equal to You take 1 upon CH plus 1 upon CC with negative sign outside, integration of U into dA, where area is varying from 0 to A. You have upper limit A minus 0 multiplied by U, it is U into A with a negative sign as it is. Now here we need to substitute the values of CH as well as CC. I am reminding you here CH is nothing but heat capacity corresponding to hot fluid, heat capacity corresponding to cold fluid. It is nothing but the product of mass flow rate and specific heat corresponding to hot fluid as well as cold fluid respectively. Now the total heat transfer rate is given by Q is equals to m dot H into Cp of H multiplied by TH1 minus TH2. Now m dot H into Cp of H can be written as C suffix H, and m dot C into Cp of C can be written as C suffix C. Now if you see here, TH1 inlet temperature of the hot fluid is greater than the outlet temperature of the hot fluid. Hence we have considered TH1 minus TH2. Whereas for cold fluid, the cold fluid has gained heat, hence the exit temperature will be greater than the inlet temperature. We need to consider TC2 minus TC1, where TC2 corresponds to exit temperature of the cold fluid minus inlet temperature of the cold fluid. Now out of this, if you take the expression for 1 over CH and 1 over CC, 1 over CH is nothing but this TH1 minus TH2 upon Q, and 1 upon CC is nothing but TC2 minus TC1 upon Q. Because both we have equated to Q, CH 1 over CH is this upon Q, and 1 over CC is this temperature difference upon Q. Now we are going to substitute the same. So ln of theta 2 by theta 1 is equals to minus UA into, this is nothing but 1 over CH, and this is nothing but 1 over CC. If you multiply the negative sign to the inner brackets, you will be having UA, Q has been taken out. Make some arrangements such that TH2 minus TC2 will be coming in one bracket, and TH1 minus TC1 will be coming in the another bracket. Now Q, if you consider Q is equals to UA, we have defined this as theta 2 and this as theta 1. So UA into theta 2 minus theta 1 divided by ln of theta 2 upon theta 1. So this will be in terms of watts. Now I can write in general Q is equals to UA into LMTD, where LMTD is theta 2 minus theta 1 upon ln of theta 2 by theta 1. In your heat transfer data handbook, it is given that LMTD for parallel flow as theta 1 minus theta 2 divided by ln of theta 1 by theta 2. And in many textbooks, they have referred the same. I'm telling you, theta 2 minus theta 1 divided by ln of theta 2 by theta 1 is equivalent to theta 1 minus theta 2 divided by ln of theta 1 by theta 2. It makes no difference once you change the suffixes 1 and 2 with respect to 2 and 1. So in general, we got Q is equals to UA into LMTD. This LMTD corresponds to parallel flow. The same equation will be used in counter flow also. Again, the LMTD you will be having theta 2 minus theta 1 divided by ln of theta 2 by theta 1, or theta 1 minus theta 2 divided by ln of theta 1 by theta 2. The only variation is in case of counterflow, this theta 2 and theta 1 will vary according to the inlet as well as outlet conditions that we will see. Now, this is the counterflow heat exchanger schematic diagram. If you see, theta 1 is nothing but TH1 minus TC1, TC2, whereas theta 2 is TH2 minus TC1. Now, we will be following the same steps. You know that dq is equals to u into dA up into delta t, where delta t is nothing but th minus dc, and this dA is nothing but the small elemental area for analysis. U is overall heat transfer coefficient. Now, after energy balance, you can see we have considered minus m dot h into cph into dth. This is corresponding to the heat transfer out of a hot fluid, and the heat transfer out of a cold fluid or heat transfer to the cold fluid is minus m dot c into cpc into dtc. If you see, we have considered minus sign for both the fluids. If you see the diagram, you will understand that. Now, for hot fluid, along the length of the heat exchanger, the temperature is dropping. Now, you are considering, when you consider dT, it is TH2 minus TH1. So, this is a negative value. Similarly, along the length, the higher temperature is TC2 and the lower temperature is TC1. Here also, if you go along the length, the temperature is dropping because the fluid is flowing in the opposite direction. You just need to substitute the value of dTH as minus dQ upon CH and minus dQ upon Cc for cold fluid, where Cc is nothing but heat capacity corresponding to cold fluid. If you substitute the same, if you follow the same procedure that we have followed for the parallel flow, you will end up with the same expression, that is Q is equals to UA into LMTD, where LMTD is theta 2 minus theta 1 divided by ln of theta 2 by theta 1. I'm repeating, it is same as theta 1 minus theta 2 divided by ln of theta 1 by theta 2. It makes no difference with the value. With this, I will stop here. In next class, we will consider a couple of problems on parallel flow as well as counter flow heat exchangers. Thank you.